I like to think about algebra as the zen of mathematics because it has to do with relationships and balance. And this notion of balance is the idea of equality. Too often when we think about algebra, we think about all these crazy symbols and lots of rules about what we can do with these symbols, rather than thinking about it as a language that's describing relationships. And that's because many of us learned algebra procedurally. We learned what the symbols were supposed to mean, and we learned some rules about how we can move those symbols about on the page instead of a structural view, which is about the meaning. And for example, this is some things I learned procedurally. I learned things about canceling. We'd have equations, and I did this thing called canceling. I didn't know why. I learned a rule: what you do to one side, you do to the other side. I learned all these rules about what I could do with those symbols. I just saw one recently that made me very upset. This idea of ditch. You ditch the 2, you ditch the 21. So here's just examples of rules that we learn, and that does not help kids in any way with meaning. What I'd love to see happen instead is kids to develop what we call relational thinking. So seeing the relationships between values. So how do we get there? The two big ideas in that are understanding what the equal sign means, and then understanding equations and allowable transformations we can do to equations. I like how Jim Caput describes the difference of the procedural view and the structural view. He talks about symbols and looking at symbols versus looking through symbols. So if you think of a person looking at this page, this is a picture. This is a math worksheet, and it's got lots of algebra symbols all over it. In a procedural view, we just learn what those symbols are, and we learn the rules for moving them about, but they don't really mean anything to the learner. I want to contrast that with looking through the symbols. The symbols are just a little bit of a shorthand to look at the meaning, to look at the underlying semantics of the symbols. So that's going to be our goal, is instead of having kids memorize meaningless notation, we want to create this idea of meaning. So the symbol that kids have the most trouble with is that equal sign. They don't see it as this balance of things with equal value. And we know that through lots of studies. You looked at one in the warm-up here where kids were answering this question: what number would you put in the box to make this a true number sentence? And you saw the answers 12 and 17 come up several times. So let's take a peek at the different kinds of misconceptions. All right. We've got Lucy. Lucy is very typical. Lucy sees the equal sign, and it triggers for her the answer comes next. It means now do the problem. It means, okay, go ahead and compute it. So if you see 8 plus 4, now do the problem, you get the 12. When the interviewer asked Lucy about that 5 there, she says it doesn't really have anything to do with the 8 and 4. Okay, and then I love it. She says teachers put that in to confuse us. Okay, so that's the most typical. The answer comes next. All right, then we have Randy. He comes up with 17. He just used all the numbers. He saw it was an adding problem, so he scanned it, saw all those numbers, and added them all. Okay, in fact, he says, yeah, but you have to add all the numbers. Okay, so that equal sign does not mean balance for Randy. Okay, Barb here gets the 17, but she does it for a slightly different reason. She's extending the problem. So she sees the 8 plus 4, now do the problem, is 12. And then there's a continuation. Okay, now go ahead and add 5. Okay. Um, Unlike the previous one, she's doing this in a step-by-step fashion. She says, then I had to add the 5, so that made 17. Let's take a look at where this extending the problem may have come from. Truly, I think kids are quite brilliant. They're making sense of some of the work they might have seen in class. Does this look familiar? Watch as I write out this addition problem and think about how the way I'm writing it might create that misconception about extending the problem. 2 plus 3 equals 5, plus 4 equals 9, plus another 3 equals 12. So look what I did here unwittingly. I wrote these different values as if they're equal. One's equal to 5, one's equal to 9, the others are equal to 12. They're not equal. So kids are creating this idea of, well, you just keep adding things on, and partly that's because the way we teachers write it. Now we're going to look at Ricardo, and then we're going to look at Gina, and both these students have a relational view of the equal sign. It's not an arbitrary symbol with arbitrary rules like, oh, the answer's going to come up next. But they've created their own meaning for it. So here's Ricardo. He knows the answer 7, and his reasoning is because these two sides have got to be the same. So he's seeing the equal sign as a balance, as a relationship between the two values. Okay. Gina's a little more sophisticated. She also has a relational view, but look at this. She also figured out that it was 7 very quickly, so the interviewer used some really big numbers that she couldn't compute quickly, and she goes, that's easy, it's 59. And she says, it's just 2 more because the 84 is 2 less. So not only is she understanding the relationship between the two sides, she's able to do this compensating procedure. She's compensating the values. Okay, so from this study, the researchers came up with these benchmarks for kids understanding the equal sign. So I want to share these with you, and then you're going to look at a video, and I want you to look for these benchmarks in the kids' conversation. Okay, so the first thing you want kids to be able to do is to be able to articulate what they think the equal sign means. Even if it's incorrect, at least you get them talking. And it might be something like, oh, the answer comes next. Okay, but at least they're talking about it. Benchmark number 2. This is when kids start to get a little more flexibility in their thinking, and they don't have to think of A plus B equals C. So that's the canonical form where we put the sum on the right. They're okay with something like 8 equals 5 plus 3. Before that, they'll go 8, now do the problem. Hey, there's no problem to do. Okay, so kids are okay with this different form. They're okay with identity problems like 8 equals 8, and then with these multiple add-ins. All right, benchmark number 3, that's what we saw Ricardo do, where he's able to understand that relationship between the values on either side. Okay, they have to be the same. All right, and then just a little more sophisticated is the Gina. Okay, benchmark number 4, where you don't even have to carry out the computation. You're kind of figuring out, you're able to compare those mathematical expressions. Okay, so take a look at this next video, and in it, this is the problem the kids are doing. What I want you to do is, 1, notice the pretty sophisticated conversation these second graders are having and how the teacher facilitates that discourse. It's pretty amazing. And I want you to notice the benchmarks. I want you to look for these 4 benchmarks. Just talking about what they think the equal sign means. See if they're okay with number statements in a different form, noticing that relationship, and being able to do it without carrying out the computation.